Well, good morning, everyone, and welcome to the AIPG Lunch Earn Webinar for January of 2025. I'm AIPG Executive Director Aaron Johnson. It's my pleasure to welcome you this morning. I do promise this is not a mushroom growing out of my head. It's a floor lamp. I'm at my parents' place today working remotely. A couple of quick housekeeping things. If you're applying for CEUs, the CEU certificate will be sent to the email address you used to register for this webinar. If you are trying to get CEUs for your registration in New York State, please be aware that you'll need to take a quiz, 5 questions, and you need to get 4 of those right. That is mandated by the New York State Education Department, and we have to comply with that request. We will put the link to that quiz in the chat at the end of the webinar, and you can take that as many times as you like until you get 4 of the 5 questions correct. It will be up for at least an hour following today's webinar. It's my pleasure today to welcome Steve Stokowski to give the AIPG Lunch and Earn. Steve is owner and the materials geologist at Stone Products Consultants, where he has a tremendous amount of expertise and experience in aggregates and in concrete petrography. Steve got his bachelor's degree from George Washington University and has a master's from the South Dakota School of Mines. He's served extensively with AIPG as treasurer of the Georgia section, as well as being very active with SME, where he was the recipient of the Herbert C. Hoover Award from the Washington, D.C. section, as well as the 2017 Robert Picars Award from SME. He is registered or certified in Georgia, Maine, and Virginia, as well as other states. I will make one quick comment today. I find this webinar is going to be really fascinating because as a geologist, I think one of the things we understand is that modern society doesn't exist without concrete. Steve, the floor is yours.
Okay, thank you, Aaron. My webinar and my slides, basically, I have a lot of pictures and then there's some text. The text I expect you to read, and you can actually copy that as you will, because I know that if I was saying the text, you'd have difficulty keeping track of it and taking notes on it. So to start off, this is alkali silica reactivity in concrete and New England, specifically New England, which for those who don't know, is up in the northeastern part of the United States, but it is not the northeastern United States. Some people like to include New York in that, and everybody in Boston would really start a fight with you on that. And some people even include Pennsylvania. But on the right here, you see the New England states. This is Massachusetts, New Hampshire, Vermont, Connecticut, Rhode Island, and Maine. Those are the New England states. Now, starting off with some of the structures, the different kind of structures that have been affected by ASR. This is a bridge. This is a high-rise, historic high-rise. This is a display abutment with the typical pattern cracking that you get with alkali silica reactivity. And it has some leaching, and the material coming out of those cracks is both calcium carbonate and silica gel. Now that is the original concrete from the 1930s. Here's concrete that was repaired. The concrete underneath the shotcrete, was finished on this and it was used as a repair, but it continued to expand in the wet areas down at the bottom and along joints. But here, the concrete hadn't expanded by the time of this picture. So this is an abutment wing wall on an underpass in Boston itself. Now, to investigate concrete, you saw it in slabs, and you look at the patterns on the rock. And one of the things that you can see with natural gravel, which is what this is that you have a rim around it when you have alkali silica reactivity. Now, you also have a rim around it when you have weathering. So you have to be able to distinguish between the artificial, if you will, weathering in place in concrete and the weathering that occurred in nature. But you can do that if you look at broken portions of the natural gravel, such as this one, and that rim is continuous along the fractured edges here. So that is ASR. And you can see it also with some of the smaller sand-sized natural stone portions of this concrete. There's a close-up. You can see the rim around this. And some of these particles have also split along foliation, which was where the reaction occurred. Whereas with this finer rock here, which is a metasiltstone, it's porous and permeable enough that primarily the reaction was occurring on the outside of the particle. There's another fine grain sandstone, siltstone here with reaction clarification of the rim on the edge. That's what that particular feature is called. And here's a close-up of a thin section with cross polarizers and an analyzer in it, because that gives nice, pretty pictures. And that's very important when you're dealing with clients. Although if you were in grayscale, you actually see a little more detail a lot of times. But in this case, this rock on the right side here, this is about 1.2 millimeters across, and this metasiltstone here has reacted. It's expelled silica gel, which has gone into the cement paste and reacted here with other components of the concrete on the left. This is what you typically see in thin section work in concrete. And to be able to distinguish the cracks readily from the infills of the cracks, all of which are various shades of gray, you need to change the epoxy so that the epoxy is blue dyed, and you fill the voids, and then now I typically have two different scales that I'm taking photomicrographs in, and these are old photomicrographs before I had a scale bar that you could put in there. But this particular one is about 3.4 millimeters across, and the close-ups are about 1.4, 1.2. And here, this aggregate particle has expanded and cracked, and there's silica gel that's come out of it, and continued expansion, which left void space in it. It actually shot silica gel out into an air void in the concrete and completely filled that void, and then continued to expand afterwards, reopening this crack, which was then filled with epoxy so that we could get a good thin section. For those who don't know, these are cement particles right here, and they're composed primarily of two minerals when they're this, which is bellite, which is C2S, and ferrite, which is an iron aluminum silicate in here. There's also another mineral which imparts most of the strength in concrete. Now, in concrete in New England, you have ASR that occurs. It doesn't occur immediately, which is distinctive from other parts of the country. You generally have to wait at least 25 years before there's any expansion. And sometimes things are just only starting 90 years later. And the reason for this is because of different environments that the concrete's in, particularly if they're wet, you get a lot more alkali silica reactivity. If you're dry, and if that means dry, being that the internal relative humidity is less than 70%, you get no reaction. But if you have a change in use, adaptive reuse afterwards, you can then cause this concrete to be wetted, and you can have a reaction going on. In addition, the classification for this is different than you get with in other areas, and that this is the late slow silica silicate category. And this is occurring with a large variety of rock types. In New England, you basically have everything is essentially a metamorphic rock or an igneous rock, but it's usually metasomatized too. And so you have a lot of residual strain in the rock and alteration. And some of the classifications are vague then because you have feldspars in there that are altered to mica. So if you were to try to classify these rocks strictly, uh, you're coming up with a different classification. But anyway, you get continuously wet structures, dams, piers, and rivers, dams, and rivers are also retaining walls and things like that on the ocean or brackish water or piers and salt water deteriorate the most. But deterioration also occurs in relatively dry concrete buildings, particularly if you've got a high, especially if you've got a high relative humidity for some reason or another. What happens with the timing of the micro effects? I showed you some aggregate rim clarification. That's usually the first thing that happens. Then you can get paste saturation, the saturation of the relatively porous cement paste and filling of air voids. You can also get radial cracking and splitting of aggregate progressing into the paste and the concrete as a whole. So you can have expansion that goes through the cement paste around an aggregate particle and then cracking other aggregate particles that are just restraining the concrete from expansion, but their strength is not something that can resist the infinite expansion of alkali silica reactivity of the aggregate in the concrete. Now there's some confusion with classification of aggregate in concrete. There's coarse aggregate and there's fine aggregate. Now the engineers and geologists artificially classify the line between coarse aggregate and fine aggregate as the number 4 sieve. Now that's not 1/4 inch, but when you have material that's coarser than about 3/16 of an inch in sands, fine aggregate, those are often rock particles. They may not be single mineral grains. So finer than that, you may have single mineral grains that are quartz. And the single quartz grains don't seem to ever react when they're in fine aggregate in concrete. But the single quartz grains may react when they're in coarse aggregate. So they have surrounding sources of other materials. And if you have a feldspars in there or residual from feldspars, you get another source of sodium and potassium that can then be part of the chemical reaction and result in sodium and potassium silica gels, which are the ASR product. But here you can see that just about every kind of structure you can imagine has reacted. Pavement, so this is interstate and U.S. level pavement and commercial pavement, building piers. These are piers that supported mill buildings, bridge piers, bridge walls, bridge beams, retaining walls, et cetera, including some unusual things like a church steeple. Fine aggregate is similar types of concrete, but you tend to have better control of the aggregate quality for pavement, so you don't really seem to have any ASR in fine aggregate pavements. There's a whole list of reactive rock types, and there's just everything you might imagine. Some are more reactive than others. Some are very rare in New England. At number 9, I got opal. I saw one piece of reactive opal my entire career in New England. And of course, the owner complained about it and wanted to have $200,000 worth of concrete removed, but that was not a good solution. But there's other things that are much reactive. There's a lot of older quarries which supplied aggregate to concrete extensively, and these are metatufs and metarhyolites, and they were very reactive and are very distinctive in appearance and have caused problems. Quartzites are another one. One thing about alkali silica reactivity is that in the early stages of deterioration, the concrete actually isn't deteriorating, it's increased strength. And that's because it's put some internal gel into the paste, which reduces the density and improves the strength. And that is indistinguishable from the kind of strength that you get nowadays in concrete. But historically, concrete was made and would only really expect to reach 3,000 psi. So you may have 3,000 psi concrete originally as designed and expected, that after 50 years, because of ASR, is now 5,000 psi. But it's beginning to crack up at that time. And if you have a chance of ingress of water, you can have other deterioration mechanisms that add on to the weathering of this concrete. Particularly in New England, you have a lot of freeze thaw. So you may have concrete at depth that isn't freezing or thawing, but if it's at the surface, you have the whole surface of the concrete deteriorating. And this freeze thaw cracking can be really extensive in large, massive concrete, with essentially rubbleization of the concrete. And engineering-wise, you have something to determine if the concrete is not if it's extremely expensive to remove, you may be able to reuse it, but you can expect it to support any loads greater than about 500 psi, but that's pretty high. So that's a decision, but that's a decision that the structural engineer has to make. Boston is one of the largest cities in the United States, and it's a historic city, and it has high rises and residential buildings and large rail yards and everything else that you can imagine it. And a lot of these things were designed by renowned architects, and they have interesting geologic features in the aggregate. One here, this is the Prudential Center garage is the first case history I'm going to go through. This is in Back Bay, Boston. Back Bay was in fact a bay. It was filled with sand and gravel from a rail transport into that area. And everybody who worked on that during the Civil War was deferred from serving in the Union Army. So that was a cushy job if you weren't that interested in going to the South and possibly meeting a fate that your mother didn't want you to meet. This is the Prudential Center garage. And when I moved to New England, I had a project in the parking area of this garage. And at that time, it really wasn't widely publicized that there was any alkali silica reactivity in concrete New England, in New England, but in fact there was. And as soon as I saw the specimen, it starts extruding silica gel, which is what this is. So this is under pressure in the aggregate, and was it has it's hard to necessarily see here, but this is purplish aggregate and distinctive, and it's a crushed stone. And the reddish color over here is just food dye that I use help distinguish the cement paste from other things in the concrete when I'm doing something called point counting to get volume proportions. But this purple mineralite came from an historic quarry in Malden, which is north of Boston. It's the Ralph quarry. And you can see the outcrop over here. This is old machinery with wooden buildings, but they were some of the last ones that I've seen were only torn down about 5 years ago. This was actually probably torn down about 15 years ago. But besides having this purple rhyolite, which is a beautiful stone and used for architectural uses, both in concrete and for lawns, if you will, or stone mulch around shrubs. It's mostly a purple aggregate, but it's some of it is also a yellow aggregate. The yellow material is an area that has some hydrothermal alteration, and it is more reactive than the purple material. I'll go into the next case history, which is Building 54, MIT. Some people would like to argue with you that MIT is the best engineering school in the world, if not the country. And it is an excellent school. And they have a lot of historical mining engineering buildings there, and a big geology department, which is in Building 54, which is this building. The Building 54 has pattern cracking on the outside, and it was designed with this purple aggregate in it from the Royal Quarry, and that's reacting, but mainly just on the outside. As you get to the interior of the concrete work, the relative humidity has decreased, and it doesn't react on the inside because of that. But it's reacting in lower levels where you have high relative humidity in the sub basements and basements and the floors there. But field of view there is 3.5 inches, so you can get an idea of the size of these cracks. And here's the mineralite, and you can see some of the other mineral particles of xenoliths in there, and it has cracks along it, and these cracks extend out of the paste, and they've got silica gel in some of the cracks, but other cracks are open, and they've got blue dyed epoxy because of my specimen preparation techniques. Here's another image here with this particle, which is overall finer grained than the previous one, but it's got silica gel in it, which is, you can trace this crack how the silica gel goes out into the cement paste, which is what this is out here. And these are sand grains in this cement paste and the concrete, and this is a coarse aggregate particle with the silica gel crack underneath these arrows. Next case history is the Congress Street Bridge in Boston. And this is a commuter route in the downtown area of Boston. And it's been repaired since this picture, but that's what we were working with at the time. Now, this is these are concrete columns here, but they're clad with dimension stone. That stone actually came from air mass and used on the bridge. And this is a fresh water pipe coming in. So it's not necessarily that scenic when you lean over the edge of the bridge. But here's this sketch, just so you get an idea of the dimension. From here to here is about 35 feet. So you've got another 25 feet below it, and it's all wooden pilings, and there's ties in between everything, reinforcing steel that tied this mass concrete up. But there's not a lot much steel inside the mass concrete because of the time when this was constructed, which is around the Depression. So sawing the concrete, you can see immediately that these crushed stone particles have rooming on the outside. And the same thing goes with finer particles in there, like this one. That's rimmed, and that's a rock particle at sand size. And one might expect that that's either weathering or ASR rimming in the concrete. But this particular granitic rock here, next to this fine grain metasilstone, had a void, and that void is filled with this white silica gel. You can see that right off the bat from the core. Now this is NQ core, and usually when you're coring concrete, you may have larger core because you're looking for the compressive strength. But if we go back a ways, we can see the bridge. We set up a drilling rig right on the top here, and there's a space underneath this that you have to go through, but you couldn't put any sort of other kind of coring rig underneath here because there's not enough room to work. But we just welded a guide to take the core as it went through the bridge deck down into this concrete, which is what we were interested in looking at, to allow us to do wireline coring in this concrete. And we cored this all the way to the bottom of the piers. Here's another image of fractured fine aggregate with the rim on the outside, which is white in color. And if you were to pick this off with a fine needle, you can see that it's isotropic in silica gel. Now in thin section, the aggregate is not in this thin section that's reacting, but it's extruded silica gel, which is what this material is across here, and then that has gone into a void, and then later it's extruded more silica gel, which actually cracked the edge off of the void of silica gel and filled the void then with different color silica gel. These are sand particles, and all these pastel colors are due to quote misaligning the optics in the petrographic microscope so that I can get these nice pretty photomicrographs. This is about 3.5 millimeters across. Here's another similar one, but here the interior original silica gel shrank a little bit, and then that other secondary silica gel filled in around the shrunken void filled with material, and this was just lost on specimen preparation. And you can see these cracks going out in the concrete coming from some other particle. One thing that's interesting is that the water level is about here, and the concrete up here is different from the concrete down here. And in the way the ASR occurred, and that's because you're getting other effects from the seepage of brackish water into into the concrete after cracking allow it to enter this mass concrete here. And here's an example. This is almost exclusively cement paste. These are larger sizes of Portland cement, and they're about 30 to 40 microns across. Here's another one here, and this was a crack that then had silica gel in it, which is this material here, and then once the overall cracks reached the exterior of the concrete, seawater started to enter the concrete and started to dissolve the cement paste, which these are highly porous areas, which are filled now with blue dyed epoxy, which you can see. And then later expansion even split this original silica gel and down more or less the center. And there's a slightly bluer, which means it's greater concentration of blue dyed epoxy down the center there. So that was an open void in these were just saturated cement paste that had dissolved in brackish water due to sulfate attack, which is a common form of deterioration. Now up here is another silica gel filled crack going across the concrete. Here's another example. This particular is a metasilstone, which is reacting, which is up at the top, and this is oriented in true orientation. And the top is up, and underneath aggregate particles, particularly if you have concrete that is shrunk because it has too much water in it, you get something called water voids. So there were holes underneath the aggregate particle, which were then filled with silica gel due to alkali silica reactivity. And other mineral deposits also occur in there. And these are usually calcium hydroxide, but there also can be things called ettringite, which is a calcium aluminum sulfate, hydrated calcium aluminum sulfate. This shows 80 years of history underneath this particle due to ASR, in that the one of the first things that happened in this water void was that calcium hydroxide formed from the hydration of the Portland cement, and it started to fill in this void. And here are some of these calcium hydroxide crystals, which for unknown reason are twinned right there. And they're in normal polarized light, this stuff is gray besides the blue dyed epoxy, but here, because of cross polars and misaligning my optics with a gypsum analyzer of one wavelength plate in there, you get these nice pastel colors. But after the calcium hydroxide started to form, then some silica gel started to form, and that wrapped around these particles and encapsulated them. It also saturated the paste on the downside of this water void. And there's some expansion too. But the expansion eventually reached the outside of that mass concrete and allowed brackish water to enter, which is dissolving this cement paste here due to sulfate attack. It also dissolved the calcium hydroxide particles that weren't completely encapsulated in silica gel to protect them, such as these, which are smaller. The larger ones dissolved. And but you still have void space, and actually near the outside of this of these voids that are being filled with calcium hydroxide followed by silica gel, you get a fibrous mineral forming, which is ettringite forming. Here it's mixed with silica gel, and here it's just formed by itself in the void. So that's a secondary product after dissolution of this cement paste. So you got sulfate from seawater, maybe some sulfate from the cement paste because there's some is part of the component of the composition of cement, and then calcium, which is floating around in there because you've got so much calcium hydroxide, and you're forming this last mineral here, etrigite. Starts off with calcium hydroxide, which is encapsulated in silica gel as ASR is happening, and then the calcium hydroxide dissolves away. You still get some silica gel, but now it's mixed with some sulfate, which is forming etrigite, and then it's etrigite by itself. Well, it's a long history in a small, thin section, a little bit more than 3 millimeters across. Here's the last case history, which is the Fore River Bridge, which is in Quincy, Weymouth, Massachusetts. Now, Quincy and Weymouth are south of Boston, and this is a major commuter route. It's also crosses the Fore River, which had a major shipyard upstream. So they have a bascule drawbridge here. This is the split, and these draws go up, and they're counterbalanced. So you don't have too much of a motor to power these things to get them up. In fact, motors only maybe 5 horsepower. That's good design there. I guess you can see it over here. Here's the center split for the bascules, and there's counterweights behind here. This is tall. This is a concrete tower clad with stone, and these windows are in a stairwell that you can walk down. And this is a catwalk across here, and these are massive piers. And this is ice floating in the river because we did all this work in the winter. Fore River Bridge, built in the Depression here, classic WPA Eagles, Works Progress Administration Eagles. James Michael Curley. Curley's a major political name in the Boston and Massachusetts area. But this, where this plaque is, this is all cracking up and expanding, and then deteriorating more because of freeze thaw, which is water that's entered this concrete because of the cracks. Now here's the problem. This particular drawbridge in the middle of the commute would be lifted, not because they're sailing a warship out, which has been in the shipyard, because this was a major shipyard, because there's small sailboats there which have masts, and people in the interior of the U.S. don't necessarily know that boats have the right of way over cars. So whenever a boat comes up there, they're required to lift this drawbridge, regardless of how many people are affected, because the drawbridge won't go down. And that was a big problem. So there was a lot of hue and cry and complaints about this. But the cynical me would say nothing really happened for 20 years because there were no fatalities associated with this. But in fact, nothing happened for 20 years because they were blaming it on the wrong thing. They were blaming it on poor motors, poor gearing, poor gearboxes, and all that. But this would be jammed, and they would strip gears, and the motors would burn out, et cetera, et cetera. Back to the bridge. Now I'm going to point out something right here underneath this bridge. There's a catwalk there, and here's a head-on view on the catwalk, and another bit of ice floating downstream out to the ocean is to the left here. And you can see there's railings up here. Now, when you go closer in, you can see these railings again. And because of the fact it's on seawater and rust, this looks pretty nasty. There you go. When I walked out on this catwalk, I noticed this railing was bent. And I thought, oh, that's pretty interesting. Why did they tie off on this railing and pull it out? And then I went to the next railing, and it's bent the other direction. And they didn't tie off on that. That's inland. Nobody tied off on that. These railings are bent because these piers are expanding. And these railings were jam fit in here, custom fit, and they were deforming because of the expansion of the concrete. The outside railing wasn't bent at all because this isn't really affected by the expansion of the concrete. But these are telltale indicators of the expansion because they're in between these piers. Again, that's the area that you can see the bent railings right there. Now, right up in this area, there's a gear that supports the bridge. And here it is. This just rolls back and forth. There's a big counterweight to the back there. So you got square pegs, if you will, going into square holes. And this is supposed to fit more or less perfectly with some clearance on the outside. But here you can see some of the example that this is rubbing a little bit. Now that little bit of rubbing wouldn't affect much of anything, but it's seriously rubbing in places, and you've got some of these teeth are being sheared off. And this is cast iron. You just don't do that. But that's where it's jamming in there. Now out here, it's just riding smoothly on that. Out here, there's 150 tons of dead pigeons and pigeon guano. But that doesn't do anything as far as this. But it does make it resistant, make people not want to go up here and look at it. But being a good consultant, I went up there just to see what was going on, and I found that out. Now, there's another image of this where it was hitting and shearing, and that's where it was jamming. I actually told these guys, I said, you could solve this problem right now if you just went up there with a grinder and ground a lot more clearance on there, and then you wouldn't have this commute problem because the drawbridge wouldn't be stuck up, wouldn't be jamming. But that was not paid attention to because we really needed to find out why it was jamming there. We did a lot of work, months and months of work pouring this concrete to see why. But here you can see where the relative concrete was reacting and pushing. Now on the outside here on either side are these piers, and they're essentially immobile. So the center pier is expanding both directions. The outside is expanding both directions, but it's restrained right here. So all the movement goes to the inside, and that's what is forcing these railings to be deformed and the teeth to be sheared on the gearing. And that's where the binding occurred on the inside because everything moved towards the inside. I calculated out how much allowance they would have allowed for thermal expansion from minus 50 to 160 degrees Fahrenheit up here, and the expansion of the concrete as determined from these railings. It's the same. It actually exceeds the amount of expansion that you would have designed it in for thermal expansion of the sill superstructure. So we got a drawbridge that's sticking up in the air, and then you can get it released and you beat on it. And so we did a lot of work and cored everywhere. 24 cores. These are long cores too. These are not something that's only a foot long. We're talking stuff that's maybe 25, 30 feet long. 267 feet total coring. Measured the compressive strength, did chlorine analyses, and did petrography on a lot of this concrete. And besides the bridge, you got wing walls and all that are there. And you can see the pattern cracking in the walls. And we cored this stuff here too. And here's just one example of the cores. The compressive stress normally would have been, apparently for this bridge, they were designed to be 2,500 PSI plus. Now that's from the depression, so they would probably be about 3,500 PSI now. And but they've gone up to 6,900 PSI, and that's quite a bit, and more than the original design. Part of that's due to saturation with silica gel, but some of them also, that's just the cores that maintain cohesion. On the average, it's about 4,500 PSI, but some of this is you got to wave your arms a bit on the interpretation, because even though we did our best to not have any large aggregate particles in these 4-inch diameter cores, and you're supposed to have particles that are less than 1/3 of the core diameter. And we looked on the outside and we just selected portions with small areas with the core that are intersected. But in fact, you could core 4-inch particle and miss part of it and just hit the end of it and then not see that. And so that affected that. We had to reject that as far as the analysis, but we had everything broken down. But when you start prepping this stuff, you can see silica gel filling voids around the outside of the particles. So it's quite obvious with some thin sections and areas of more silica gel. This reactivity has been going on for an extensive period of time. And look at the multiple layers in this layered silica gel here. As before, when you get into the concrete, you can see plates of calcium hydroxide and water voids underneath particles. Now this is also a metasiltstone, and you got these are unusual sulfate mineral forming there. Here's etrangite in this air void here, and you got dissolution of the cement paste here, and this is residual cement paste that hasn't been dissolved yet. Here's a coarse aggregate particle. That's a metasiltstone. It has saturated paste on the outside. Below the saturated paste, it's got peripheral cracking here, which is this crack that's filled with blue dyed epoxy. And the water void underneath of this one is completely filled with silica gel. But because we've also had some seawater entry into this is below the water level, you get dissolution of cement paste with residual portions of cement paste here. And the blue dyed epoxy here is saturating the cement paste, which has been dissolved, and that's why you see a paler blue color, but you see some of the cement particles that did not react with the sulfate solution from seawater in there that are still present, plus probably some fine particles from the sand and coarse aggregate, which were in the cement paste. Here's another example of dissolved cement paste along a crack, which has got silica gel on the outside of the crack, which apparently was split in half, and later silica gel, which went down the center of the crack. But it's hard to tell the sequence here. These are cement particles, and this cement paste out here is very saturated with silica gel. There's another water void filled with silica gel underneath, and coarse aggregate metasiltstone particle here. And here's a geopedal structure. This was above the water level, and the silica gel was dripping out of this coarse aggregate particle and then forming a little stalactite. That's a geopedal structure, and one of only a couple that I've ever seen, which indicate on the structure itself which way is up. And this would be all just gray with blue dyed epoxy here. But because of the way I adjusted the optics, it has this nice pink pastel color to it. Here's another case of water void underneath a coarse aggregate particle and a siltstone. And here there's silica gel mixed with ettringite in there, which is given it this fibrous type appearance, and over here plus and higher birefringence. Now, after all this work, what can you do? Well, there's an issue here in that this is a major commuter route. You can't just put them 15 miles away and not have that road just destroyed. You have to maintain traffic flow. So they built another bridge, which you can see the edge of which is here. But this is a temporary bridge, all galvanized steel, very, very expensive. And here's the Four River Bridge, the original one we were seeing, which is being torn down. Now, the concrete here disintegrated easily underneath of it. So in areas here where these abutments are, you know, they were just, they weren't even crushed. They were just broken up into small pieces with heavy machinery, some with drop balls and some not at all. And this concrete was not reused at all. But here's the first bridge that was built. They built a whole new bridge so you could build the major bridge that you wanted afterwards. So they built this over a course of a couple of years. This is a temporary bridge. Major commuter route. So this substructure here is not galvanized, but everything up top here is galvanized because they didn't want to have any problems with it. And this, by the way, is the Salem, which is the display ship now, which is a World War II cruiser. There, Salem is 40 or so miles away from here, but this is the best place to dock this ship. And it's right down from the historic Four River Shipyard in Quincy. Here's a bridge which was finally finished. And I went and saw this last fall around Veterans Day. And so this is a much different bridge. This whole thing will lift all the way up, which they do. which they have to do for sailboats coming out, but the cycle time is a lot faster than the original Fall River Bridge. And this is architectural coatings on it. It's not painted, but it's a much more durable structure. And not only that, the wing walls, a lot of them were replaced, but some of them didn't have that much ASR in them, so they weren't. Here's another view where you can see that there's no traffic congestion because this bridge will open up and down right away when needed to pass sailboats, which is really the only thing that goes through there now. So that's about $1 billion total what it costs for this. Now, in summary, at the end, there's ASR sites all through New England. There's at least 20, 25 in the Boston area, and you're out going into Western Massachusetts and Vermont. These are dams up here that have ASR. Stuff in New Hampshire, dams, mill piers, dams here, a couple dams that were removed by Central Maine Power here that expanded. They tried to cut a slot in them to take up the strain, and that just didn't work. So they had to remove them. This was in Rhode Island. This was a U.S. level route where concrete was taken out, which had ASR, which causes the slabs to buckle. Here's a couple ASR instances in Connecticut, and the Connecticut DOT will tell you that there's no ASR in Connecticut because the DOT controls the cement composition in Connecticut, but they don't control the cement composition for some municipal and almost all commercial work, so they can have ASR in Connecticut too. So that's it in summary, and here's how you can contact me. And if you have any questions, we'll address those questions now, or you can take your exam.
The link is available in the webinar chat. I do see one question in the chat, and due to time constraints, we'll try to answer that question. And then, Steve, is it all right if people email questions to you if they have them?
That's fine. I will answer them.
Yeah, please do that. And great, please do that. We will proceed here with Norman Meeks's question. He says, so with concrete that is expanding due to ASR, what are feasible options other than full replacement? Can you use a sealant to limit the contribution of the weather, or could you remove a layer and then add a stronger veneer of concrete? And then his second question is, how is this paid for? Is it the state? Is it insurance? How do folks cover the cost?
I don't know anybody that's managed to get insurance money to deal with ASR affected concrete. And the reason is well, it's just not something that's covered by insurance. But as far as repairs go, with a heated structure, a high-rise building, you can prevent ASR if you dry the structure out by putting a semi-permeable membrane on the outside or a coating. Now that's a siloxane. That's not a silicate. That's a siloxane on the outside. And that's done successfully in Iceland. It's been done successfully for maybe 35, 40 years in Iceland. And that just allows the concrete to dry out internally in a heated building. Now, bridges and pavements are not heated, and dams are not heated. So there's no apparent, you can't use that as a solution to it. Things like pedestals for statues in Iceland, where they've coated those with siloxane, they've just continued to deteriorate. They have planters around the buildings. The planters were coated, the planters all deteriorated, but the building did not. So they had to adjust their style of construction so that they did not have concrete in those particular features because they would not go below the relative humidity of 70% for the concrete. You can't put a coating on the outside of the concrete and expect it to survive. One of the first images they showed was of a retaining wall for an underpass in Boston, and that was shotcreted. It was adhered to the concrete, and everywhere they continued to remain to get wet again, the concrete expanded and broke up the shotcrete. Now, I think you could possibly decouple a surface from the concrete underneath if you didn't have that much of a durability requirement. You're able to completely redirect water away from the interior concrete. But that has not been done ever. But it would decouple the surface concrete. So that would be panels basically if you put on the outside. Inside would still continue to deteriorate, but if you're able to insulate it and not have freeze thaw in the interior, then you would limit the complete fracturing of it. But it would be, I don't know, maybe temporary but still life of structure type of repair for it. Now, people in dams have tried for a long time to try to deal with ASR in dams. And if you have a gravity dam, you're basically not going to fix the problem. If you have another kind of dam, it may eventually reach confining pressure that you're going to have limited ASR and you can get 300 years of lifetime out of it. But if you start to cut slots in it, which has been done in Maine and around the world extensively in Canada, it just doesn't work. Technical solution that doesn't work. So that's it. I think we're exceeding our time.
Yeah, thank you, Steve, again very much for providing the webinar today. It was quite enlightening. If you need CEUs for New York State, please remember to log on and take the quiz. That link is in the chat. Otherwise, I hope we see you next month, February 25th, for the next edition of the AIPG Lunch and Earn. Thank you all for attending.
Thank you.